In this lecture, we will study about the various networks after connecting the sequence impedances which we have studied in our previous lectures. So first we will study the positive sequence and the negative sequence network, and after that we will study zero sequence network. So what is a positive sequence network? It is simply the network in which we show that only positive sequence currents are flowing, and the impedances which we show in the network are the impedances which are offered by the network to the flow of positive sequence currents. Similarly, in the negative sequence network, we usually show only the negative sequence impedances. Now, in this system, usually in the power system, what we assume that the system is balanced until some unsymmetric fault occurs there or some unsymmetrical load is connected there. So usually it is assumed that up to that point where the unsymmetry is present, the power system is symmetrical in nature. So because of that, what we achieve is that this assumption of balanced system gives us all the this sequence networks to be decoupled, that is all of them are not linked with each other. As we have seen in our previous video, that whenever the load is balanced, that is when the self impedance for various loads, let us say ZAA is equal to ZBB is equal to ZCC is equal to Z self are equal. Similarly, the mutual impedances ZAB, ZBC, ZAC are equal, let us say Zm, then this type of load is called as the balanced load. And we have seen in our previous lecture that for such kind of loads, the sequence impedances and the sequence networks are decoupled. What does it mean? It means that we can represent the sequence matrices. Let us say this is VA0, VA1, VA2. Now I can represent these impedances in equivalent form where it will be Z0, Z1 and Z2, and all other entries will be 0. And here will be the zero sequence current, the positive sequence current and the negative sequence current. Now clearly we can see that for VA0 I can just write Z0, IA0, VA1, Z1, IA1, VA2, Z2, IA2. So you see that the flow of one type of sequence current only generates a voltage drop of that type of sequence. Like positive sequence current is developing a positive sequence voltage drop only. The zero sequence voltage drop is not depending upon the positive sequence current or the negative sequence current for a load which is following this property. However, if a load is such that it is not balanced, then we will find that there will be terms like this, that let us say it is Zx IA1 plus Zy IA2. Clearly in that case this VA0 is depending upon IA1 as well as IA2 also. So for the assumption when the power system is balanced, we can safely assume that the sequence networks are decoupled, or that is the one kind of current will flow in on the same kind of network only, that is zero sequence current will flow in the zero sequence network, the positive sequence current will flow in the positive sequence network, and the negative sequence current will flow in the negative sequence network. Now since we assumed a balanced system, what does it mean when the positive sequence or negative sequence currents are flowing? Let us say that this is a delta connected balanced load, star connected balanced load Z, 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 and it is some neutral Zn to ground. Okay, now let us say it is connected to balanced voltage source through some, let us say, Z neutral. Now, when the source and the load is balanced, that is system is balanced, we can safely say that this neutral point, let us say N, and this neutral point, let us say capital N, these are at same potential. Even if we connect these two points, neutral points, there will be no current, that is this current will be zero. I can safely remove this wire also. So you see that in such a scenario, the neutral at any point of the power system, even if I add some other load which is again symmetrical and balanced, then in that case also this neutral point, let us say N1, will be at the same potential as that other 2 points if it is connected to the power system. So for a balanced system, whenever there is a flow of balanced currents, since positive sequence currents are balanced in nature, similarly negative sequence currents are also balanced in nature, so their flow will not cause any difference in the potential of these points. So it is safe to assume that in our positive sequence or the negative sequence network, the reference bus for the various voltages will be the neutral of the system. So this is a very important point. You should note it that for positive sequence and the negative sequence network, the reference is the neutral of the system. Now, the only difference between the positive sequence network and the negative sequence network is that we assume that all the generators usually generate positive sequence balanced voltages. So as we have seen in our previous videos, that whenever a phasor system or a three-phase system is balanced, then it is not going to have any other sequence components. If it is, say, let us say, balanced in such a way that it is having positive phase sequence, then it will have only positive sequence component. The negative sequence will be 0 and the zero sequence will be 0 if it is a balanced one. Similarly, a system which is balanced but having negative phase sequence, then it will have only negative sequence component and all other will be 0. That we have seen in one of the examples in our previous lectures. Okay, so everything is quite same. However, what happens in the negative sequence network, we usually change the impedances offered by the rotating machines. As we have seen in our previous lecture, that the impedances offered, the positive sequence impedance offered and the negative sequence impedance offered can be different in rotating machines. However, these are not different for static machines or the static components like transmission line and transformers. Okay, so what we do, we draw the positive sequence network. Usually what we have studied till this lecture are the positive sequence networks only. So we will draw the positive sequence network of any system. Like this is a system. If I want to show the positive sequence only, then what I will do, I will show just a source, phase to neutral, and the per phase impedance. So this is one kind of the positive sequence network for this kind of system. Now, to change it to the negative sequence, what I will do, I will just delete this source, because we are assuming that the sources present in the power system are generating positive sequence symmetrical or the balanced voltages. Okay, so this impedance will be changed to only the negative sequence impedance. If it is just a static device like some transformer, then the equivalent impedance will be same in both positive sequence as well as the negative sequence network. Okay, so in this way we can find the negative sequence network of any power system just from its positive sequence network, just by putting the voltage sources to 0. Okay. Now in the next slide we will discuss about the zero sequence network. As we have seen in our previous video that the zero sequence impedance for static devices can be different than the positive and the negative sequence impedances. Like for transmission line, usually what we find that the zero sequence impedance is around 2 to 3.5 times of the positive or negative sequence impedance, and this ratio is on the higher side for double circuit lines. Okay. Now if zero sequence current is flowing into the system, what does it mean? It means that all the currents are having same magnitude as well as same phase. Now if this is current I, similarly this current is again I angle 0. I am just assuming 0 angle 0. Now the currents are same in magnitude as well as the phase. So if there is no neutral point, let us say it is not closed. Okay, so what will happen? According to KCL, at this point all these currents should be equal to 0, or if I want to draw it in some another form, what I will show, I will just show like this: E angle 0, it will be E angle 0 if it is generating some positive sequence, zero sequence voltages only. Although in the power system there is usually nothing which can generate zero sequence voltage in a usual power system. Okay, so what is happening here now? This is some impedance of the line, this is some impedance of the line, and this is some impedance of the line or this load. Okay, now you can clearly see here that if this is current I angle 0, this current is I angle 0, and this current is I angle 0, it can only flow into the system only if there is some point connecting this to this. Otherwise, if this is absent, then according to KCL, all these three currents should be equal to 0. Now the definition of zero sequence is IA plus IB plus IC over 3. Now if there is no neutral connected, then it should be always equal to 0. So you can clearly see that the zero sequence current will be 0 whenever there is no path for their flow into the system. Okay, like if the neutral is not connected, if in this case the neutral was connected like this, then zero sequence currents would be having a path to flow. Similarly, if this was the case, like this neutral was grounded and this neutral was also grounded, then again the zero sequence currents will flow this path, flow in this path from this point, like from this point to ground, and from ground to here and to this point. So they will have a closed path. So in this way, whenever there is a path for the flow of zero sequence currents, only then these can flow into the system. Now what about the reference bus for the zero sequence networks? Now you see that this is the neutral to ground impedance. Similarly, this is again neutral to ground impedance. Okay, now the zero sequence currents are flowing into the ground also. Okay, so even if there is small impedance of the ground, then let us say it is distributed at various places, since ground impedance is actually distributed. Okay, so if there is a flow of current in the ground, then there will be voltage drop across these distributed impedances. So the voltage at this point of the ground will be different, at this point of the ground will be again different, then this, and then this. So you see that in a zero sequence network, neither we can take this neutral as a reference, because the potential of this neutral will be different as compared to this neutral in the power system. Similarly, this ground will be having a different potential voltage level at various other points. So what we assume? We assume for zero sequence network, the reference as, let us say, I want to find the zero sequence impedance and network. What I will do, usually for transmission lines and other equipment, whenever there is some impedance of ground, it is usually taken care of into the zero sequence impedance only. Like for transmission line, this zero sequence impedance is including the impedance of the wire as well as the effect of ground also. Okay, similarly in every case the effect of ground is taken. So if I assume a reference having or being of a conductor with zero resistance, okay, this conductor is having a zero resistance. Let us say this is a reference. Now if I start connecting various equipment or items of the power system like this, and this is again some other part. Now these impedances are having the effect of ground also. Okay, so at any point if I want to find the voltage, if I want to find any voltage with reference to this reference bus, what it will give? It will actually give the voltage of this point to the ground, since already it is having the effect of ground considered in this impedance. So this voltage drop will have the effect of ground also. So this point or any this point, what it will give? It will give the potential of this point with respect to ground. Okay, so in this way, this is the reference for the zero sequence network. Now here can be other, this voltage can be different and this voltage can again be different. So these two voltages can be different. However, this point is at the same potential of this point. This conductor is having zero impedance or resistance. Okay, now usually the zero sequence impedances are different from the positive sequence and the negative sequence impedances. So the zero sequence network is quite different as compared to the positive sequence and the negative sequence network. Now for example, what we will do in the next slide, we will try to show the sequence network for balanced star connected load, balanced delta connected load, and the star connected load will have a neutral in one case and in other case it will not have a neutral. So we will see that thing in the next slide. Let us first take a case of a balanced star connected load without any neutral connection. So it is balanced, it is Z, it will be Z and it all will also be Z. Okay, so if only positive sequence currents are flowing, so with respect to this neutral, the per phase impedance seen by the current will be just Z. So this will be the reference neutral for the positive sequence network and this will be the per phase impedance seen by the current. So this is the positive sequence network for this load. Okay. Similarly, if negative sequence currents are flowing, then again it will see only Z as the per phase impedance or the impedance with respect to its reference bus, because for the positive and negative sequence the reference bus is the neutral of the system. So again it will be like this only. This is the neutral. Okay. Now as we know, if this neutral is not connected, then the zero sequence current cannot flow into the system. Okay. So to show it, what we can do, let us say it is any reference of the zero sequence network. We will show an open circuit, that is the impedance shown is infinite in the value. So there will be no zero sequence current into the network, and this will be the zero sequence impedance that we have studied in our previous lectures for various kind of equipment. For if it is a transmission line, it will be around 2 to 3.5 times of Z1 and Z2. If it is a synchronous machine, its value will be very low as compared to the positive and negative sequence reactance. Okay. However, there will be no connection between the line and the reference bus of the zero sequence network, and this reference bus is actually not neutral. Here it was neutral, but it is not a neutral. Okay. Now what will happen if I connect this thing to ground with an impedance, let us say Z and Z. Now I will also show a source. Now let us say what I have done, these sources are generating zero sequence current only. Okay. So if I want to see the potential of this point, what it will be with respect to this ground, VAG will be simply I0 ZG, and the current flowing in this impedance, what it will be, I0 I0 I0, 3 times of I0. So 3 times of I0 into Z and G. It will be Z, not ZG. Okay. So what it shows that if I write it like this, I0 I take common and I write it like this, Z plus 3 times of Z and G, then I will get the same value. But it shows that the impedance offered to zero sequence currents, this will be the zero sequence voltage only. The impedance offered to the zero sequence current is equal to the zero sequence impedance of the equipment plus 3 times of any impedance connected between neutral and ground. So the positive sequence and the negative sequence network will remain same because it is a balanced system. So all the impedance per phase impedance seen by positive and the negative sequence currents will be same. However, for this zero sequence, what will happen? The zero sequence current will find an impedance equal to the zero sequence impedance of that equipment, like transmission line or the transformer or the generator, and the 3 times of the impedance connected between the neutral and the ground, and this will be the reference bus of a conductor with impedance 0. Now you can clearly see that at this point, what I am going to get, I am going to get the true value of the voltage of this point with respect to ground, as I can clearly see here. This voltage is with respect to the true ground. Okay, so this is the reference bus, and this is going to give me the voltage of this point with respect to true ground. Since now I am already considering the effect of ground in the zero sequence impedance of the network only. Okay, so anytime whenever a zero sequence current is flowing into the system, then this will be 3 times of any impedance connected between the neutral and the ground. And for positive sequence and negative sequence, even if any impedance is connected between the neutral and the ground, this will not appear into the network. So positive sequence and negative sequence network will not have any impedance connected between the neutral and the ground. So I hope this point is clear to everyone. Now we will try to draw in the next slide the sequence network for delta connected balanced load. Let us draw a delta connected load, balanced delta connected load. That is, the impedance in every branch of the delta is equal Z, Z and Z. This is a three-phase system. Now, for a three-phase system, for positive sequence and negative sequence network, we have reference as neutral. Let us say this is the line, this is the line, this is negative sequence and this is positive sequence. Now, the impedance per phase, that is with respect to line and neutral, will be found if I convert this delta to equivalent star. That will be Z by 3, Z by 3 and Z by 3. So with respect to this reference, this is the reference, neutral is the reference. So the positive sequence line current and the negative sequence line current will find a per phase impedance with respect to neutral of Z by 3. So you should clearly remember this thing. Now, what will happen to the zero sequence current? Clearly, this delta can be considered as a super node, so there is no return path. So the zero sequence current cannot flow. Okay, so it is clearly said that there will be no connection between the reference bus of the zero sequence network and the line. It will be open. Now, there is one more thing, that there cannot be any zero sequence voltage drop. This will always be zero in the delta connected system. That is, line to line voltages cannot have zero sequence voltage, because the sum of line voltages, even if it is unbalanced, it will be always equal to zero according to the KVL. We are starting from the point A, we are ending at point A. So the total potential difference is zero. So the voltage between the lines cannot have zero sequence voltage drop, even if these are unbalanced. Okay, so let us say somehow I have put a source in this delta which is generating zero sequence voltage. Similarly, I have put here also and here also. Okay, so this voltage source will try to create some current. Now, clearly there cannot be any zero sequence voltage drop between this point and this point. So from KCL, I can clearly see that there should be some current I0 in this branch such that E0 minus I0 Z will be equal to 0. So the zero sequence impedance seen by the current will be E0 over I0 equal to Z. Okay, similarly, if this is the voltage source creating some zero sequence voltage, again this current will be I0 such that E0 is equal to I0 Z0. That is, any potential rise in a branch will meet with the same potential drop in the same branch, such that there cannot be any zero sequence voltage drop across the lines. Similarly, this will be I0. So you can clearly see that there can be zero sequence circulating current into the delta, this I0, this I0 and this I0, but it will be circulating such that the potential rise is equal to the potential drop in the same branch. Okay, so this circulating current is going to face this impedance every time. So what I can show is in the network is like this. This is the zero sequence impedance seen by the circulating current, and the circulating current will circulate in this only if somehow some zero sequence voltage drop is generated or induced into the delta branch. Okay, usually we don't show this zero sequence voltage drop or voltage source in the circuit because usually there is no such kind of voltage source generating zero sequence voltages. So for delta, this is the zero sequence network. So in this way we can draw the zero sequence network of any network given in the question. Now in the next lecture we will try to solve a numerical example for finding the zero sequence network and the positive and negative sequence network of a delta with mutual coupling. However, that will also be a balanced system only. And the next lecture to that we will try to find the various connections of various kinds of transformers in the zero sequence network. As we have clearly seen in our previous video that for transformers usually we take Z1 is equal to Z2 is equal to Z0, but still this Z0 is connected in different ways according to the connection, whether it is star delta or if it's delta star is connected to neutral is connected to ground or not. Okay, so based upon the type of connection, this Z0's connection into the network will depend whether it will be a open circuit or closed circuit or something else. So that we will see in one of our next lectures. So if you find that this lecture is helpful to you, then please share and subscribe my YouTube channel. Thank you.